Okay, welcome back, everyone. I hope you had breakfast. Yeah, so this third lecture will work on the exercises. But actually, first, I just wanted to show you some plots for the monolith, just because they're cool. So this is what I was trying to plot yesterday. And each of these vertices here is a point we run numerically. So if you remember, there was this functional with some NAs. So for each NA that you point in different ways, you get a point here. And you get this 3D shape. So for instance, this point here is a non-Gaussian model. And this is showing you how the primal and dual approaches are really complementary. So the blue lines are allowed regions you get by putting more and more parameters in your ansatz for the amplitudes. Then the red ones are the dual ones. So when you do the most simple ansatz for the dual function, you get this outer shape, and you know everything outside is excluded. And you go towards the optimal bound, which is this black line as you increase the number of parameters. So yeah, this is just to show you some real plots. Now let's go back to the exercises. So yeah, there were some silly typos, but the important one is that in the very last equation, you don't need some extra pole that was there in the file. And yeah, the way we will do it is that I want you guys to try on your own with some computer. So if you don't have your computer here, just do it in group with someone. Because otherwise you don't get that much if I just show you the solution. Yeah, so we did the first two yesterday. The third one, you can do it in your notebook. Sorry, in your, it's also called notebook in Mathematica, in paper. But the rest are numerical, and I want you to try alone. We can meet in, I don't know, 25 minutes. You can come ask me questions. I can go around and yeah, to see how it's going. Okay, so just in case it's not clear, M without anything is the external mass, which I'm setting to 1 at some point. And MB would be if you have a bound state. Okay, I think I will start giving the solutions. Given the questions, let me just say a few things. So this rho variable, or R, is just a way to write an amplitude which has these cuts. It's an ansatz for an analytic function with those cuts. Okay, that's one thing. Then what else should I say? Let's just go to the mathematical file. Where is it? Here. Let's make it bigger. Okay, so that was yesterday's. This is a nicer plot for what this z variable and the analytic bound does, taken from this paper. Let's see the third exercise quickly. So the idea is to basically multiply the amplitude, which has these poles, by this function. Why? Because, you know, if you set S star to be the value of the bound state mass, then you will cancel the pole. And this is still bounded at the physical domain or the boundary of the disk. And then you end up with the same problem as before. You have a totally analytic function on the disk whose maximum value can be just 1 because of this maximum modulus principle. And going back to what the function was, so this is what I wrote here. you're now bounding this f of z where you are canceling the pole. You will get f of z equals 1, which means s is just 1 over the z variable. And okay, that gives you this residue. Let me know if there are questions. So, okay, for the numerical bounds, let me get the first thing is to write this row of ansatz. That's trivial. Then you want to write a grid in which you are going to evaluate unitarity. So I gave you one way to do it, which experimentally works well. That is a grid that is denser close to threshold, where you expect the amplitudes to have more dynamics. And infinity, so that you give enough bounds at large energies. So it's just basically in this disk using Chebyshev zeros that give more points close to here and here. And then you translate to S. So this is what this function does. So for instance, the Chebyshev grid from 0 to pi is something like this. Looks like this. And then if you translate to S using this function I gave you, it gives you these values for when you have 20 grid points. So you see many close to 4, and then some big numbers. Okay, so now let's do the non-bound states and maximize something inside. So you can write an ansatz. You can even use like 3 variables. That will work as well. So you give some constant, which will be like the A0, that in this case is just S evaluated at 2n squared. That's a parameter. And then these ANs, which are also parameters. And this is what Mathematica will vary to get the optimal bound. And then these row variables. So you can just use variables to read what the variables are if you evaluate this at some number. And then the idea is to create a table of these unitarity conditions. So you make a table, you can give some I epsilon so that Mathematica doesn't screw up which branch you're supposed to get from the square roots. And just do abs or, okay, some complex expand where it's the same as abs, and set that less or equal than 1. And you do this for many points in S. That is this unitarity grid we had here. And then you just do this, and you see you get the right answer, which is a constant. That is the free boson S matrix. And it sets all these AN coefficients to 0, because the amplitude is just a constant. You do find minimum, or find max of minus the amplitude. And you get -1. So you can plot, okay, here you know very clearly because it's setting it to 0, but you can also plot it for a range of S and see that indeed it's just a constant. I know some of you got it. I'm just curious to see how many. Can you raise your hand? Okay, cool. This is like the test one. Once you have this, then it should be easier to get the other ones. So now let's do the bound state. So since now you have a bound state, you need to put some poles. So you put a pole at some value, mb squared, and the crossing symmetric pole. Now I'm defining this function that depends on the position of this pole, the mass of the bound state. So I have an extra variable, which is the residue that I want to maximize in this case. So I do the same trick. I do a table of the different, well, the amplitude evaluated at different physical points. I define some function that does this maximization procedure for different bound state masses. You can just do a table, it's fine. This is to get the replacement, because as you saw, when you do this for, say, 3, you will get the maximum G as the first entry, and then the replacement, that is the optimal solution. So it's just to get the replacement. And okay, this is to see where we are. And we make a table, it's really fast, because I had run it before. But no, it's still very fast. So you see, you take a table of the different bound state masses and what the maximum coupling is. Close to 0, you get 0, it grows. It actually should give you an error at some point. So just so that you see it live. Okay, now it's live. You make a table. You see it goes very fast. At some point, it says the problem is unbounded. And we know at 2, you have this issue of the screening of the poles. So it's true. And you get this plot. Any question? Did anyone get here? Yeah, raise. Be proud. Okay, so this is for the maximum coupling. Now let's compare to what we know is the analytic solution. So we define this sine Gordon sorry, amplitude. And then we can plot both of them for a given bound state mass. So this is what we got from numerics, from this solve function. And this is the sine Gordon amplitude with some, again, with some I epsilon, so that Mathematica knows how to take the square roots. And you see they're just on top of each other. So there are actually 2 plots here on top of each other. If you go to lower bound state masses, then you get the minus the sine Gordon. So you flip the sign, and they're on top of each other. You can also go to on physical S and see the plots, sorry, the poles. So if you plot between 0 and 4, you just see these poles explicitly with opposite residue. And you can also plot in the complex plane using something like density plot for the absolute value. And you see, you get these poles between 0 and 4. Okay, so that's for the bound state. Then for the leaf, we can use the same ansatz we had before, this S of S with just the expansion on these raw variables. And you can plot these bounds in different ways, get the bounds in different ways. The simplest one can be to maximize, say, S of 3.9, where you fix the value of S2. So it's just a way to scan this space. So the way to do that is to give it another constraint to Mathematica. So you have the unitarity ones, but now you're also giving it this constraint that you're fixing the value of the amplitude at some point, and you're maximizing at another one. So this is for the maximum. We know there is this symmetry where you can flip the sign of the amplitude, so we know we should get just minus the other thing, but okay, you can do fine minimum. You run, it's also very fast. Why is it different? No. Okay. Because I gave few variables. Sorry, let's do 10 again. Oh my God. Never mind. Let's go back in time. This is what you should get. So then if you fix this S2, this amplitude at 2 to be -1, you should be here, and this gives you the free fermion. So you get S0 equals -1 with everything set to 0. So this is just a constant amplitude -1. The same for 1, this other point at the cusp. It's just free theory. Then if you do something else, so for instance, set this value of S equals to 5/2, you will have something like this if you plot S from 0 to say 10. So you see you have some zeros here. So you can locate precisely where the zeros are using something like find root. It will tell you, okay, I have this 0 at 3.8 something. And as I told you yesterday, the function that gives you this bound is actually just the CDD0, which is 1 over the sine-Gordon amplitude. And the parameter there instead of the pole will be the 0, so you can give this value that you found. And indeed, you get the same function. Now, what happens, this is for singe cordon that I said is on this side. What happens here on the other side for the staircase? If you plot, say, at -2/10, which is on this left-hand side, then you don't see the function crossing 0 between 0 and 4. Why? Because actually these zeros went into the complex plane that you can see explicitly with this density plot. So, okay, again, you can locate these zeros. They're crossing symmetric, so they should be at some value like this. And compare with this CDD0, where you give this value, and you get the same. Did anyone got the leaf? Did you get it in the end? Cool, cool. Okay, and for the duo, I don't know if you even got to read the part, but the main thing is to just discretize in some way the integration. So there is something called quadrature that I think it's very standard. So you implement these polynomials and integrate over the polynomials that you know how to do. And this is how you would evaluate this integral over the absolute value of k. And depending on what you're trying to bound, k will have different analytic structure. So for when you are trying to find the maximum value of s, say at 2m², you should put a pole, as I derived yesterday because of this Cauchy contour deformation. So a pole with residue 1, this is what this ansatz is doing. And these extra factors are here to make sure that k decays fast enough at infinity. So it's just an ansatz for k. Let's see if it's done. You can check that indeed it satisfies this anti-crossing solution, that the pole is 1. These are the variables. Now I call b these variables. And this is the implementation for the weights. When you, if you look at equation 7, I'm approximating an integral by a sum with some weights, where I evaluate the function and then multiply by some weights. So this would be the weights. I'm just making a polynomial, a polynomial in big X. And then I will evaluate the function of these values, little x, j. So, okay, you can work on it if you want. And this is a dual functional, which is supposed to be an integral over the absolute value of k. Now I turned it into a sum with some weights, where I evaluate k at some grid points. And these funny looking variables is just a way to go from x from -1 to 1, where it's very easy to do the polynomial integration, to s, that goes from 4 to infinity. There is some Jacobian here. These are the grid points where you evaluate just Chebyshev's zeros. And you can minimize this dual functional and get 1, which is what you expect. Because indeed, you can do it numerically. Analytically. This integration where the dual function is this gives you 1, which is the maximum value S can have. Now, if you do it for this bound state case, then what you're asking this dual function to be is something that is 1 at the bound state mass. So this is what I'm giving here. Well, actually 1/2 because you pick up the poles, the 2 poles, the 1 at m and 4 minus mv squared. So they sum up to 1. This is why I'm putting 1/2 here. And yeah, this is the same functional we had before, except the analytic expression is different. And this extra factor, again, is so that the integral decays at infinity. So, okay, you can do it for many MVs. And I think what's really cool, it's running with different MVs. I'm doing it for many cases, so it's actually faster than the primal one. What's really cool is that even putting just one variable, so one free parameter here, b, already gives you this blue curve telling you that everything outside it is excluded. So you're really bracketing the optimal bound. And already with just 2 parameters, you are basically on top of the bound of the optimal one. And yeah, the last thing I was telling you is to get from these dual variables the amplitude, which at optimality is given by this. So you can plot it first for this bound that you get with just 1 parameter. Okay, it's not great, but it's 1 parameter. You see, at least it has the correct behavior, more or less. If you do it for 2, you already get something very good that, okay, for the imaginary part, at large values of S, it's not great. If you do 8 parameters, then it gets closer, etc. So yeah, it's if you want to do numerics, the dual is very good. And yeah, that was the last problem. Do you have any questions? Okay, I hope this demystified how this Bootstrap works in practice, and that it's actually, okay, for 2D, 222 is quite simple. But in higher dimensions, the idea is the same. Numerically, it's much more heavier, but the idea is the same. Okay, so if there are no questions, we can end.
Okay, excellent. Let's thank Lucía.